Ooh, done with the first video recording and then realized that I was using the wrong microphone and the audio quality is very, very bad. So I have to do this again. Yeah. Um, some time ago I made videos about longitudinal and transverse wake field simulations and said that I would show how to calculate the loss and kick factors, but I've never really got into that. So in this video, that's what we're going to be doing. So I've already gone ahead and made a 9-cell Tesla cavity based on the original geometric factors, not geometric parameters, not geometric factors, geometric parameters, and already run my simulation. So for my simulation, I offset the beam. I think you could. Okay, you can't. So I offset the beam so I can excite transverse modes, because if I should leave the beam in the, like I explained earlier, I hope I did, um, moving the beam just through the center like this, it doesn't excite any transverse mode. So because I want to calculate both the loss and kick factors, um, from this I offset the beam. Now in Wakefields, you see the wake integration method and then the wake integration part. So I haven't added any shift to the part, so you have two parts: the beam moving through the part which is defined by this, and then the integration part. So basically, if you should go to the help, the integration part is the part that you want to integrate your wake potential over. So to get the either loss or kick factor, so if you should integrate along the axis, it's the loss factor, and then if you integrate along the an offset, it's an offset axis is the kick factor. So yeah, so these were my settings, and then my sigma is 100 millimeters, so that's my bunch length, and then the total charge is 1 e2 minus 9, so 1 nanocoulomb. So once you're done running your Wakefield analysis, you should see 1D results and then particle beams, and then you should see your wake potential, of course, and charge distribution, everything. But then to get your loss and kick factors, you see this wake integration info. If you double click on it, then you see your wake loss factor. Now because there was no shift, so my integration part was not shifted, you have that the shift is 0. So what I'm having is the wake loss factor. Now I already copied the typical result for the kick factor. So if you should offset your integration part using in CST Studio, so when you define your particle beam, then CST would calculate the loss factor, the kick factor, and the kick factor X, and also the kick factor Y. So in this simulation, I don't think it was exactly this geometry. I offset my integration part by 5 millimeters in the X direction and 5 millimeters in the Y direction. So this is what you would have. But then the problem is that if you wanted to kind of do a study, like for me, currently I'm interested in seeing how the loss factor varies with the bunch length. I have checked, and then there was no way I could access these results from the post-processing templates, because every time you typically do a sweep, and then every time the bunch your bunch length changes, this is overwritten, and there's no way to store it. I even exported the results, and I couldn't. It wasn't among the exported results. I also looked for if I could find it here to access this result, but there was no way to get this information. But then, fret not, there's a way you can actually do it yourself, so you get exactly the same result yourself in just using post-processing steps. So before that, we'll go to the documentation and then see the definition of the loss factor. So the loss factor is just an integral of the charge distribution, the charge distribution, and the wake potential. So the product of the charge distribution and the wake potential. And your kick factor is your transverse wake potential multiplied by your charge distribution, then scaled by the normalized by the offsets that you gave. So going right into it, first thing before we start, I would want to, okay, I think I'll just start and then make the corrections on the way. So first we want to get this product. So first thing we want to get this product. So your charge distribution as a function of distance multiplied by your wake potential as a function of distance. So this S parameter. So if you should go to CST, you have your charge distribution distance and then you have your wake potential distance. So first I'll be solving for the loss factor. So we want to combine these results. So we go to general 1D and then mix template results. So the first one is charge distribution distance and as a function of distance, and then wake potential, yes, distance. So I have A multiplied by B, and that should be it. But then you notice something now. If you should check the charge distribution, it is given in coulombs. Your charge distribution in coulombs per meter. Now we need to normalize that. So we have to divide by the total charge, because if you should check your units, this is already in voltage per picocoulomb. So this should be in per meter, so that when you integrate, you have that meters cancels that. I mean, your unit of length cancels this out, and then you just have your V per coulomb. But then what we are having here is coulombs per meter, so we have to normalize this by the total charge. And how do we find the total charge? We integrate the charge distribution. So for that, we go to general 1D result still, and then go to 0D or 1D result from 1D results. And then we want to perform an integration. And then what do we want to integrate? Charge distribution. So when we integrate this, I'll just call this total charge. I have this is recording, yes. So call this total charge and then evaluate. Now you see that this is 1 e2 minus 6, but then our total charge is actually 1 nanocoulomb. I think this has to do with the fact that we are still working in still in millimeters that we're working, of course, but yeah, and then this axis is in meters, but then this is in millimeters, so kind of some unit discrepancies. But then I'm not concerned with this, because in the end, like, everything cancels out. So I'm not concerned with this. If you're working with meter, I think you would have exactly the same results. So I'm not concerned in trying to get this to be the correct units for now, because you see that this is a factor of 1 e2 minus 3. So because I need this total charge, I need to divide this product by the total charge. I move this up. So I move this up and then I edit this. So this becomes divided by total charge, which is divided by C. So I could call this wake potential scaled, because it's scaled by the is it scaled? I don't know. I think I'll just call it scaled by the charge distribution, and then I put L for longitudinal. So that's it. So what next? It's just the integration. So when I want to integrate this, so I go to general 1D and go to 0D 1D result, and I want to perform an integral of what? WSL. So when I do that and I evaluate, I should get my loss factor. Oh, something is wrong. This shouldn't have taken so much time. What's it saying? Oh, I haven't evaluated. I haven't evaluated this yet. So if I should evaluate this, I could clear my error also. Then I have this, which is the product of the charge distribution and the charge distribution. I think is this? No, it's not convoluted. It's multiplied by the wake potential. So this is the result, and so now I can perform my integral, and then yes, so the value you can see is 0.0000107, so that's 1.077 e to minus 3, which is what you have here, 1.077 e to minus 3. So that's your loss factor. Now I could just call this K loss. Now for the kick factor, I need to do the same thing, but then charge distribution multiplied by the wake potential, transverse wake potential. Now you have transverse wave potential in two directions, and as you could see from here, CST gives you in the X and also the Y, but then I usually take the average, so I will just do the average to here, but then you could calculate each of them separately. So I'll just copy this, copy to clipboard, and then paste from clipboard, and then change this to WS transverse, and oh no, I'll change this to kick. Okay, kick. So I have to edit them. So since I need X and Y, I would move this to D, so total charge to D, and I will make this potential X and make this potential Y. So I have A multiplied by B plus C, then divided by 2. I hope I'm not messing up any of my brackets. Yes, and then divided by D. Hopefully I didn't mess up any of my brackets, and then I could evaluate it. Yes, so this is what I have. That looks weird. X plus Y divided by this here. Well, I think that's it. I'll check. I'll check the result later. So yeah, that's the distribution, and then you have the kick. I have to change this to integrating WST, and then if I should evaluate, okay, something is wrong. This shouldn't be the result. I think I made a mistake with mistake. So here's wake impedance. Supposed to be wake potential Y. Yes. Evaluate. Okay, yes, so this is it. I think this should be correct now, and then when you evaluate, yeah, 0.05. I knew because I've already done this before, so I knew that the result was 0.05. But then if you should check the units of this, you have that what we have currently is voltage per picocoulomb, because your Y is given, your weak potential Y is given in voltage per picocoulomb, and your transverse wave potential in the x direction is also given in voltage per picocoulomb. So this integral is in voltage per picocoulomb, so I could just indicate that here, voltage per picocoulomb, but then we want voltage per picocoulomb per meter, which is why we have to normalize with the offset that we put. So I put an offset of 5 millimeters, so that's offset here that you have. So what I want to do is to mix a result, so I mix temperate results, and then I want the K loss in V per picocoulomb, then divided by, so A, then divided by offset, and then now since I want it in meters, I will do multiplied by 1 e to minus 3, and hopefully that works. Yes, so 10.42. You could also view the results in 0D. So this is the loss factor. I'll close this now, and then okay, I have to rename this, but I mean it's not necessary, but I want to. So this would be K, kick, V, picocoulomb, meter. Okay, so this is 10.4, and the loss factor is 1.07 e to minus 3. Now I don't know how many of you are familiar with ABCI, but then it's a 2D code that you also use for Wakefield analysis, and I'll put a link in the description so you see where to download the 2D code from. Now comparing with the results from ABCI, yes. So this is the result from ABC, and then you see that the loss factor is minus 1.08 e to minus 3, which is pretty close to what we have. We have minus 1.077 e to minus 3. And then for the kick factor, what do we have? For the kick factor, we have coming. So for the kick factor, we have 1.015 e to 1, so that's 10.15, and then what we have from CST is 10.42, so pretty close. Now I don't know which one is more accurate, but then I think if you should refine your mesh for CST, I think maybe you would get closer to this value from ABCI. Or maybe this one is more accurate because the mesh is already pretty dense, currently 592,000 mesh cells. So that was it. And one thing I need to mention lastly is that to calculate the loss and kick factors, you do not need to run your wake for a very long time. So your simulated wake length, I mean, for ideally maybe for three sigmas, you could already calculate your loss and kick factors, but then I use 10 sigmas. And that is because if you should look at your charge distribution, you have just values here, and then on either sides of it, it's 0. So even if you have for 1 kilometer wake length, it will still be 0. And then you can see this from your product. So where's the product? So your WSL, you have zeros, and then here you have something which is what we're integrating, and then the other from about maybe 600 millimeters upward it's also 0, or from 400 millimeters upward it's 0. So this is what you're integrating. So even if you solve for a kilometer wake length, you still have your charge distribution multiplying everything out with 0. And then you notice the same thing for your transverse, the product of your charge distribution and your transverse wake potential. So yeah, that's that. And yeah, I don't think I'm missing anything. Okay, and with this, you can now do your sweep, and then you have your results saved as post-processing. Now I don't know if any of you knows how to get the wake integration infos from here and be able to use it for your sweep or something. And if you know, you could always leave it in the comment, but for now I do not know, and this is the method I use. So yeah, that was it. Bye.